record. We're day 3 of chapter 8. For those that are watching online, you're missing a lab, so you can't recreate it, so good luck. But you all that came in took one of those cups of M&Ms, you measured it to the nearest ounce or tenth of an ounce, and you wrote that down to be used slightly later. Do not eat them yet. And don't forget, let me do this now, that what you are weighing is technically more than M&Ms. Yeah, so I will tell you the weight of the cup is 0.06 of an ounce. So you'll have to remove that from your total ounces of M&Ms, 0.06. Yeah, so you measured to the nearest tenth. This is actually 100th, so the cup is 0.06 of an ounce. All right, so your answer will be now to 100th once you get rid of the 0.06 of an ounce. All right, but what you're going to start with is this. I would like you to calculate, and I couldn't decide what level of a confidence interval to do, so we're going to do different ones. So for, let's see, who do we have on this side here? 2s, 3s, and 4s, and 5s. So 2s do a 90%, 3s do a 95%, 4s do a 98%, and 5s do a 75% confidence interval. Got it? 6s and 7s. 6s do a 90, 7s do a 95. And then over here, you guys do a 98% confidence interval. So you're going to construct a 98% confidence interval for the true proportion of red M&Ms. You'll each have your own cup.
What percent?
I gave a different one for different groups, so you'll have to remember whatever number I said, because I don't remember. And then when you're doing this, include all the steps. Like when we did averages, you had to either have a sample size of over 30, or you had to know the population was normally distributed. For a proportion, it was different. And if you don't remember what that was, glance back at the notes that we had from the last time we met, where the different conditions you had to go through, include a picture, include a formula, and if I can, I'll see if I can actually pull that up and display it if I have it on my computer, or on my iPad right here, of what those conditions were, and having a picture. You'll do the formula, the numbers into the formula, then the actual interval, and then an interpretation of that confidence interval. So that's what you're going to do right now with your groups. I'll go and see if I can find that actual slide. So then after I've said this to those in the class, but online now I'm talking to them. So after you've counted the number of red M&Ms in your little sample, and then your total number of M&Ms, that'll be the information that we'll use for today. The ounces that you measured earlier, we're going to use for a later idea. But after you've done that, then this is our process, our procedure that we're going through. Very similar to what we did when there was the slide related to doing averages for estimating mu. Here we're trying to estimate P, a confidence interval for proportions. So 1, is it a simple random sample? Generally speaking, for those that saw me do it, I had a giant bin of M&Ms and I stuck the cup in and dished them out. More or less a random selection of M&Ms. 2, finding NP and NQ. When I presented this in lecture the last time, I said NP, another way of thinking about NP is, it's the number of successes. So in this case, we're counting red M&Ms. So your NP is how many red M&Ms that you had. And as long as you have at least 5, and then NQ is the number of failures. So you had a giant slug of M&Ms. You had way more than 5 failures. I don't think anybody had an entire cup of red M&Ms. But the NQ is the number of failures. So in a problem like this, you would say, I was given a random sample of M&Ms. There are this many successes, whatever you had. What were some examples? How many red ones did some of you have?
7.
9, 7, 11. One person had 3. Okay. So if you don't have 5, you would then have to say, since there are not at least 5 successes, or 5 failures, but in this case it was 5 successes, there were not at least 5 red M&Ms, I cannot assume the sampling distribution of p hats is normal. At which point I cannot calculate a confidence interval. But for the sake of argument for today in class, even if you're in that case, you're going to do it anyways. So you'll say, I'll proceed with caution, or when I get my results, I know they probably won't be valid, but for the sake of doing the problem, I'll do it. But for everybody else who got a number over 5, you'd say, well, there were this many successes, which is over 5, this many failures, which is over 5. Therefore, the sampling distribution of p hats will be approximately normal. Do I have to say all that? Yes, you do. That's a lot of writing. I know, because it's about communicating effectively. So when you find the number of successes and failures, then you make all that really long statement about, therefore, the sampling distributions of sample proportions is approximately normal. If you haven't written that down, I'm going to pause. You should write down a statement similar to that so you're in the habit of doing it. Depending on what confidence level you were given will depend on the z-score that you use in the formula. So now, if you've done this, hopefully you've been looking at your whatever confidence interval I gave you. You draw a picture, normal curve for p hats. And really what I'm actually going to do is I'm going to do it for z first. The center of a normal distribution is 0. A normal distribution is centered at 0. The standard deviation is 1. So if you're using the applet online, when you load it right away, that's what it comes up to, 0 and 1. And then in the little red area will depend on which one you were given. So if you were given a 90% confidence interval, or confidence level, I should say, if you were given a 90% confidence level, did anybody find the z-score for that? 1.28155. And that would be a negative one because it's left of the 0. And the other one would be to the right, so it would be positive. So if you're doing a 90%, that's the number you got. We've done 95 before, so if you were given 95%, it's like 1.95996. All right. If you were given something else, again, the key is when you're doing it in your calculator or on your computer app, if that middle part is 90%, that means the tail is 10%, because the whole thing has to be 100%, which means each tail, this one would be 0.05. That one would be 0.05. And then you'd be finding your z-score correspondingly to whatever you're going to use. And then you pick whatever your p hat was. Someone want to shout out what their p hat was? Just anybody at all? What was your proportion of red M&Ms? 9 over what? Who had 9? What was your total number of M&Ms? So 9 over 64 would be his p hat. And what was your confidence level? Which one are you guys assigned to? 90? 98. So for a 98% confidence interval, what was your z-score? 2.326. Okay? That sounds about right. And then your standard deviation of the sampling distribution, also called your standard error, would be then taking your p hat, 9 over 64, multiplying that by your q hat. So it's going to be over 64, and that's minus the 9, so 55. Dividing by 64 again, and make sure that you have this whole thing under a square root. So when you're doing a proportion, that's going to be like the most amount of work. Now, on the StatBlue website, does it give me a one sample? Yes. If you're on the StatBlue website, in the middle column, top item mine's green on my computer. I don't know if it's the same on all of them. It says 1 sample confidence interval for a proportion. So once I get to here on my screen of all the work I've done pretty much without needing a computer, except for finding my z-score, after we do this, put it, showing the formula, putting the numbers into the formula, then you can go to the StatBlue website. And the StatBlue website, it says sample size of n. So for the one that we're showing here on the screen, that's 64. Sample proportion p hat will be 9 out of 64. And then it asks for what confidence level. And then it will actually spit out all that information for us online. And so for this one, it says, it gives me the values of 0.0579, comma, 0.2656. And as I've said before, if you look at the interpretation on the StatBlue website at the bottom, that is a model of how not to make a correct statement. Because on the website for the StatBlue, it says there's an approximately 98% chance that the true population proportion lies somewhere between 0.0579 and 0.2656. That is a wrong understanding of confidence interval. So instead you would say something along the lines of, if this were you, so the one person in the classroom, I am 98% confident that the actual proportion of red M&Ms, context, got to have context, the actual proportion of red M&Ms is somewhere between, and now you could either do it as a decimal or a percent. If I'm explaining this to people who aren't in stats, I'd probably make it a percent because people think they understand percents. I would say I'm 98% confident that the true proportion of red M&Ms is between 5.8% and 26.6%. So again, that's you're spanning nearly 20% difference from top to bottom. That's a wide interval difference. Why is the interval so wide? Does anybody have an explanation for why a 98% confidence interval is going to be so wide? If I have a wider interval, it's like when you go fishing. If I want to be more confident in getting a fish, I want a bigger net. And that's the similar idea to a confidence interval. If I want to be really confident, like 99% confident, that also means I'm going to have a really wide interval. But that also means, it depends on what you're talking about, it might not mean as much if you have such a wide interval. If you're trying to pick presidential candidates, you don't want to be plus or minus 10%. Like, that's a big variation. You want to be narrow. All right. So the other way to go about it, too, is we did these with the class. Some were 75%, 90, 95, 99. The bigger the confidence level, the higher the Z value. All right. Because a 90% was 1.28. 98%, 2.33. What was a 75% Z-score? Group that was 75%? What was your Z-score for 75%? So if you get on that applet page, then you're thinking about, if I had a 75% confidence interval, what's on the ends is 25%. Split between the two ends, half of 25 is 12.5. 12.5% as a decimal is 0.125. So if I'm on that applet page for a normal distribution that comes up with a mean of 0 and standard deviation of 1, in the red box I type in 0.125, and it yields a z-score of either, depends on if you're left or right, negative 1.15, 035. So this top one is 1.15, 0.035. So a much lower confidence level, 75%, means my z-score is a much lower number as well, which means I'm going to have a much narrower interval for my estimate. The other way to narrow my interval, if I can't do anything, if I'm like, I can't change my percent, if I want to be at a certain interval margin of error, the only other way to make your interval narrower is to increase your sample size. If I have a larger n, as you look at that formula up there, if n is bigger, so if you have a fraction and you keep making the denominator bigger and bigger and bigger and bigger, the fraction gets smaller and smaller and smaller and smaller. So then whatever I'm plussing or minusing, if I increase n, this gets smaller, so that means whatever I'm plussing and minusing gets smaller. And that will narrow the interval as well. And most people will figure, like, how can I be more confident in something? Well, I just sample more. If I sample more, I should be more confident, which is true. But it's not just confident, it's actually called precision. As I sample more, I get a more precise answer. Precision means I narrow that interval. Confidence means I widen the interval. So it's this balance between being really confident and also being precise and deciding where in that spectrum you need to be. With that in mind, I'm going to assume you created your confidence interval. So here's what I'm going to tell you now, is that the actual proportion of red M&Ms is 20%. It's supposed to be 20%. Did anybody have an interval that was not 20%? Like, when I mean that. So if you did your interval and 20% is not in this interval, right? So the one that we constructed was between basically 5.8% up to 26.6%. 20% is in this interval, so this interval does capture the true proportion. Did anybody's interval not capture the true proportion? And I'm not terribly surprised. Now, if we had all done a 75% confidence interval, I would have expected probably 25% of us would not have got the actual true proportion in there, because that's just how it works. If you make many intervals at 75%, about 25% of them will not include the true proportion. That's just the nature of how confidence intervals work. We did a lot of 90%, 95, and 98%. There's just not that many of us in this room to create that many intervals to have one or more miss the mark. So now we'll just go ahead for everybody in the room. We'll all do a 95%. But in order to do this, we need to have a data set. So it says create a 95% confidence interval for the average number of M&Ms per ounce. So this is where you counted your total number of M&Ms. What'd you have over there? You had 64 M&Ms. Is that right? Yeah. All right, so the one person that we were talking about here, that one person had, wait, how many again? 64 M&Ms. M&Ms per ounce. What was the weight of your? 2 ounces. Did you subtract away the weight of the cup? No. The weight of the cup was 0.06 ounces. So yours was 1.94 ounces. So then you're going to calculate what is 64 divided by 1.94. And we're going to go to the nearest hundredth. 32.99. What everybody's going to do in the class right now is find your number, which won't take you long, and then we're going to make a list on the board. And then for every person in the room, that's one data point. We should then have over 30 data points. And then we can do this as a class. So go ahead and find your number. So having 24 samples from class, I'm not at the magic number 30. So here's what I do know, though. The t-distribution is what is called robust. What robust means in this sense is the t-distribution can handle some skew, but not outliers. So although we don't know if the population distribution is normal, if we did, it wouldn't matter the sample size. Since we don't know anything about the population distribution, we have to look at our samples and say, well, did I have at least 30? If the answer is no, I then look at the data set, and I'll actually teach you some tools to use. One of them is called a probability plot. There's a couple other things that we can do to prove whether or not the data looks like it came from a normal distribution. And as long as it's somewhat bell-shaped, which means there can be a little bit of skew, they're actually going to be more skew than you would believe, you can still use the student's t-distribution, as long as there aren't any outliers. So we look at that 27.55. That's the only one that's like, wow, that was very different. And it might be an outlier. If it is, then we can't use the student's t-distribution. But for sake of today's argument, we're going to say we can, so that we can actually calculate this out. So what I want you to do then is take that data, go to the StatBlue website, stats.blue. You're going to click on one sample t confidence interval, and you're just going to need to just crank it out and put those numbers into your computer. And then we're going to construct a 95% confidence interval. So go ahead and take a moment and enter those numbers. For the sake of your neighbors, try not to be saying them out loud unless you're whispering to do back and forth. Otherwise, you're just like, stop saying numbers while I'm trying to type numbers. So after we get all of this data plugged in, I choose a confidence level, which I said choose 95% on the StatBlue website after you enter it all in. And then you hit calculate. Now, assuming that we all entered our numbers the same way and didn't have a missing decimal place or typed in, like I know for one of my data points, instead of hitting 33, I hit 22, but I noticed that, so I went back and fixed it. So validating that your numbers are the correct numbers. So what I have, again, this assumes that I entered it correctly for our class here. My X bar was 32.98. Now, if yours is off from that a little bit, then maybe you just had a slight variation in a number you put in there. If yours is off from that a lot, then either I made a mistake in entering data or you made a mistake in entering data. What I like about the StatBlue, like right now, I can see that at least all my decimal places are in the right place. Because that's another mistake. You actually enter, 329.9. That's going to really skew the data. But then it tells me the interval that I created with the data that we brought together from class today would say that I am 95% confident that the average number of M&Ms per ounce would be somewhere between 32.38 and 33.59 M&Ms per ounce. So the interval that we had, let me write it down here on this page, we said it was 32.38 to 33.59. And what that says is I'm 95% confident that the actual number of M&Ms per 1 ounce is somewhere between 32.38 M&Ms and 33.59 M&Ms. And then the nutrition information on the back of a package indicates that the serving size is 1 ounce, which is about 32 pieces or 32 M&Ms. What does our confidence interval do with respect to what's printed on the back? And the reason I ask this question is this is actually getting us to what we're going to be starting in the next chapter. The statement that was made in class is our interval starts at 32.38, which let me go ahead and share this on the screen. So our interval, 32.38 to 33.59, was the average number that we calculated. And on the back it said that we should expect there to be 32. Since 32 is not in our interval, then our interval would basically be saying that their claim is false. If they say it's 32, we're actually saying it's more than 30. It's between 32.3 and 33.59. From a consumer's point of view, would you rather it be this way or would you rather it be the other way for the average sample size? That is, what if they told you that it was 34, but we said it's actually this? As a consumer, does that make you happy or sad? If it's this, does that make you happy or sad? Happy, because if they say it's 32, but I know I might get at least one more M&M per serving. This goes to the fact that I'm sure you all count your M&Ms when you're eating them, right? Yep. Every time. So if I were the Mars Corporation and we did some sampling, we determined that it's actually more than 32, but not a whole lot more, I as a corporation would say, I am okay with that. Because if someone were going to do this and find it's the other way around, they're going to say, hey, that's not right. You're not giving me what I'm paying for, or whatever else that might be happening. But also, remember, we only did a sample size of 24. So there could be that little bit of variability from those next 6 that might have an impact on this interval that could make it slightly wider, or not. We don't know. That's the nature of statistics, is we're playing in this land of gray, mathematically speaking. Because we go, well, how is this? Now, what I don't want you to do, and what you need to be really cautious about, is it doesn't matter how far outside the range this is. It's either in or it's out. And if it's out, then we say that the claim from the company is wrong. Well, you could go ahead and sue them and say that they're giving us more M&Ms per ounce than we thought we were. But that would also mean more calories per serving, which then that means they're the result of me being fat. Because I eat M&Ms on a regular basis, I actually might have some fault in there. But when people do make claims and try to sue things, so in the last minute here, I'll explain. So there was one, so I used to live north of Chicago, and there's a Six Flags in Chicago called Six Flags Great America. There was a young girl who rode a roller coaster ride who, in the process of riding it, choked on something she had in her mouth. I can't remember if it was gum or a candy. She got off. She'd already suffocated. She died. Family sued Six Flags Great America to say that the roller coaster was operating out of compliance and it was pulling too many G-forces. She couldn't handle it. It was their fault. The ride had been tested, of course, or proclaimed to have been tested. So we happened to be there with our school on National Physics Day, and we had these little vests that had accelerometers in the vests. And so we were at the roller coaster place, and these guys show up in their suits doing, investigations. They ask what we're doing. We tell them. So they send us out, and so what we did is we randomly assigned kids to ride in different places on the roller coaster. So where you're in the front, middle, back, left, right, that kind of thing. They all collected data, brought it back, and then we pulled all the data in and analyzed what's the confidence level for G-forces on every corner of that entire roller coaster. And then our data was actually submitted as state's evidence that acquitted the state, or not the state, acquitted Six Flags because it was not operating out of compliance that day or any day because of this kind of stuff. So you might be saying, well, how is this used? That's just one example in the court of law. It's used. Things like this can be used in many different areas to say, does this happen if you get into any kind of a quality improvement or quality systems? This is where you live most of your time for confidence intervals. All right, so I'm going to say this last thing. So this goes for the one person who had a low. There is what's called the +4 for confidence intervals. The way we do it is slightly skewed, but if I were to take, instead of x over n, I would use x plus 2 over n plus 4. Why do I only go 2 in the top? Because if I have 2 more successes, that means I have 2 more failures. If you do this for p hat, we actually get more accurate results. All right, and that's what's called the +4 rule for constructing confidence intervals for a population proportion. I'm not going to go into the derivation of how we know that this is more accurate, even though we're adding numbers that aren't part of my sample. We actually find that this gives us more accurate results when we're doing confidence intervals. And it's called the +4. So it would be saying, a question would say, hey, now do that same thing, but use a +4 confidence interval. So it's knowing that, well, that just means I add 2 to the successes, and I add total of 4 to the denominator, and I do everything else the same. And you're going to get a slightly different, although in this case, because of the consolidation of our data, not that much of a difference in what our confidence interval would have looked like.